Paper 1, June 2020. So we've got a graph here, and if we look, all of the concentrations, partial pressures, amounts of each of the gases seem to level off. That's when equilibrium is reached. So it's asked you to draw on an appropriate axis when the mixture reaches equilibrium. Well, when implies time, when means time. So at what time do they reach equilibrium? Well, that's when the concentrations no longer change. So you draw a line down from when all of the lines flatten off, and all the graphs flatten off, and you mark that off as x on the x-axis. A 0.230 sample of carbon monoxide is mixed with hydrogen in a 1 to 2 mole ratio and allowed to reach equilibrium. So I've got 0.23 moles of carbon monoxide. I've got twice that, because it's in a 1 to 2 ratio, 0.46 moles of hydrogen. It says at equilibrium I've got 0.12 moles of carbon monoxide, which means that if I started with 0.23 and I've now got 0.12 moles, I've used up 0.11 moles of carbon monoxide. That means that if I've used up 0.11 moles of carbon monoxide, I must have made 0.11 moles of methanol, because 1 mole of carbon monoxide makes 1 mole of methanol. And if I've used up 0.11 moles of carbon monoxide, I must have used up 0.22 moles of hydrogen, because 1 mole of carbon monoxide reacts with 2 moles of hydrogen. So if I started with 0.46 moles of hydrogen and I've used up 0.22, I've got 0.24 moles of hydrogen left over at equilibrium. Okay. The total number of moles is 0.12, add 0.24, add 0.11 at equilibrium, 0.47. To get a mole fraction, I need to scale that up to 1 mole. 0.47 scaled up to 1 mole. What do I multiply by to scale it up to 1 mole? Well, I do 1 divided by 0.47 will give me a scaling up factor of 2.128. It's only asking for the mole fraction of hydrogen and the partial pressure of hydrogen, so I'm just going to do it for hydrogen. There's no point wasting any time on any of the others. So I've got to scale up all of them by 2.128 by multiplying them through. I'm only going to do it for the hydrogen because it only asked me to do it for the hydrogen. So 0.24 is the mole fraction times 2.128 will give me the mole fraction rather. 0.511 is the mole fraction of hydrogen. Partial pressure is the mole fraction multiplied by the total pressure. 0.511 times 1.04 times 10 to the power 4, 5.31 times 10 to the power 3 kilopascal. Given an expression for the equilibrium constant for this reaction, partial pressure of methanol divided by partial pressure of hydrogen squared, because there's 2 in front of the H2 in the equation, multiplied by the partial pressure of carbon monoxide. What are the units? Well, I've got a kilopascal on the top and 3 kilopascals on the bottom. Cancel one top and bottom. I've got kilopascal squared on the bottom. That's kilopascal to the minus 2. Some more carbon monoxide is added to the mixture. What will happen to the partial pressure of methanol? Well, I've added carbon monoxide, which is on the left. It's a reactant by Le Chatelier's principle that will want to use that up. If it uses that up, it will use it up to make more methanol. So the amount of methanol in the mixture will increase, and therefore the partial pressure from that amount of mole fraction of methanol will also increase. Effect on Kp, none. Only the temperature is the only thing that affects Kc or Ka or Kp, any of these equilibrium constants. There's only temperature that affects that, so the answer is none. State the effect of any of the addition of a catalyst. Effect on Kp, none again, because only temperature affects Kc, Kp, or Ka, any of these equilibrium constants. And why? Well, what a catalyst does is, it doesn't affect the position of the equilibrium. What it does is it increases the forward and backward reaction speeds, the rate of the forward and backward reactions by an equal amount. So overall, it doesn't shift the position of equilibrium to the right or the left. it just increases the rates of both the forward and backward reaction. It means that equilibrium is reached more quickly, but the position of equilibrium is not changed.